Hello everyone, welcome to my channel. In this tutorial, we'll be discussing about how to interface a 4x3 keypad matrix with STM32. So I think all of you have might seen this type of keypad matrix, 4x3, 4 rows and 3 columns. You'll be having 3 column pins and 4 row pins. But in order to interface, we need to look into it a bit deeper. So this is the internal diagram of the keypad matrix. You'll be having button connecting each row and each column, so that when someone presses the button, the person will be shorting particular row with the column. For example, if I'm pressing button 1, I will be shorting R1 and C1. If I'm pressing button 2, I'll be shorting R1 and C2. Based on these combinations of whether it is shorting R1 C1 or R1 C2, we will be deciding which key that the person has pressed. That is this is just like a geometrical coordinate system, where in which R1 C1 corresponds to a particular position, R1 C2 corresponds to a particular position. Based on the position, we'll be thinking of which button has a user pressed. And coming to a problem, in this keypad interfacing, we'll be facing a problem known as key debouncing. What is key debouncing is, for example, if you see here, we have all the buttons placed in the keypad matrix. So whenever a person is pressing a button, for the button to either discharge from logic 0 to logic 1, charge from logic 0 to logic 1 or 1 to 0, it will not directly charge or discharge. It will take some oscillations. For example, this is a logic 1, and whenever you are pressing button, your intention is it will directly go to logic 0 in this manner. But you are wrong. It will take some time. Like if you see here, we are getting a few oscillations before it is completely discharged to logic 0. So these oscillations will lead to key debouncing, because what happens is, if you see here, this is the logic threshold for logic 0. So whenever it is taking oscillations, sometimes the peak is greater than the logic threshold. So this is the first point, second point, third point. So whenever a person presses this button, our microcontroller will read the press as 3 times. This is what known as key debouncing. How to avoid it? Simple. We will be giving a software delay between first press and second press. For example, a person press the button at 0 milliseconds. Then we will be reading the keypad only after 6 milliseconds. That is 0.06 milliseconds. So until 6 milliseconds, if the user intentionally presses also, will not be reading it. So this is a way to deal with key debouncing. This is the only way to deal with key debouncing. And coming to the schematic for further steps, to interface STM32 and keypad matrix, we will be connecting all the row pins of keypad matrix to PB0 to 3 pins of STM32. That is, we'll be using completely port B only. And columns we will be connecting from PB4 to PB6. And coming to these LEDs, here we are using these LEDs in order to a kind of debugging mechanism for our keypad driver. That is, if our keypad driver is working well, whatever the number we are pressing, that equivalent binary should be represented with these LEDs. That is what our intention is. So coming to steps for programming STM32, as we discussed in the previous tutorials also, first we'll enable the clocks for the necessary ports, and then reset the GPIO pins that we are using, and then configure the GPIOs as input or output based on our needs, and then PUPDR, which is pull up and pull down register. This we will do for only input pins. Whatever the pins we are using as input, we will be resetting the PUPDR for that input pins, and then programming the PUPDRs accordingly. Application specific steps. Here we will be needing to develop a Keyscan driver. So for that, what we are doing is monitor the key pressed using the Keyscan driver function. Further, we will be discussing how to develop Keyscan function also, and represent the pressed number in binary format using 4 LEDs. So these are our application specific steps for this video. So coming to enabling clock, in for this video, we will be using port B for all our operations. So port B is here, so which will be 10. So 10 means 2. So we'll be writing RCC register clock control AHB1 ENR 0x002. If anyone has a doubt regarding why we are using only AHB1 ENR, click on the pop-up video that is popping up right now here. That will tell you about why we are selecting only this particular register and why only AHB1 ENR. Coming to GPIO model register, this GPIO model register will be using to set a particular pin to input as input or output. Coming to how to write a value into register, we'll always be using and equal to negation of combination or equal to combination for resetting or setting the bits respectively. If you need further information, you can visit to my part 2 of this series, which is embedded programming with STM32, in which I have detailedly explained about this. Coming to our objective, as mentioned in the previous slides, we need to make PB0 to PB3 and then PB4 to PB0 to PB3 as outputs and PB4 to PB6 as inputs, because by default what we are assuming is we are taking rows of the keypad matrix as output and columns as input. So whenever someone presses a button, we'll be reading through columns, and on rows we'll be placing some information uh, that we'll discuss in the further part of the video. And PB12 to PB15 is the place where we are connecting the 4 LEDs, so those are also need to be programmed as outputs. So coming to the programming part, so once take a look at the model register. So this is the model register. 00 will be placing for input, 01 will be placing for output, and 10 alternate function mode, and 11 analog mode. So whatever you place here corresponds to only one single pin, so these two bits corresponds to only one single bit. So what we have to do is PB0 to PB3 we need it as outputs, right? PB0 to PB3 and PB12 to PB15. So before configuring it as output or input, first we have to reset them. To reset them, our intention is just fill it with zeros. So keep these as zeros. We are using PB0 to PB3 and also PB4 to PB6. So we need to keep all these as zeros, and then PB12 to PB15 is also we are using. So PB12 to PB15. So now, as I mentioned in the earlier videos, we'll be always using and equal to negation of combination. So whatever we kept as zeros, flip them to ones and write the number that is being represented. So if you observe here, here we will be getting two F's, and here if you split it like 4 numbers a time, you will be getting 3 triple F. So our whole value will be 0x ff, and end we have 3 triple F. Remaining in the middle you fill it with zeros. So this is what the value we have to use it with and or negation of in order to reset the bits to 0 position. So that is what we are doing. We are programming it with ff003ff. And next, for treating it as input or output, whatever the pins we need it as input, we have to keep them as zeros only. Whatever the pins we need it as output, we have to pull up to 1 in motor register. So what we'll be doing is in 3ff, if you remember properly, we are using PB0 to PB3 as outputs. So we need 0 1 in them, so we get 5 5. And in PB4 to PB6 we are using it as input, so no need to change them, so you can keep them zeros as it is. And then coming to this PB12 to PB15, we need it as outputs, so again we have 5 5. After configuring the GPIO model register, now we have the pull up pull down register. So why do we need pull up pull down register and how it works and all? Again, you can refer to my part 2 of this series, where in which I explained in detail about each and every part of this. So moving further, monitoring IDR. This is the input data register. For every GPIO, we have an 16-bit input data register. Each bit corresponds to each pin of the port. Configuring ODR. This is the output data register. For every GPIO, we'll have input data register and output data register, each of 16-bit. Each bit of the corresponding registers corresponds to each pin of the port. Now comes the interesting part, developing the Keyscan algorithm. So before moving into this interesting part, I want you to look at this Proteus simulation, a simple Proteus simulation. So if you observe here, we have all the rows here, all the columns here. And what I want you to see is, for example, I have a row pin connected here, which is not powered yet. So if I'm pressing this, nothing is happening. For example, if I'm powering this row, let us say I'm switching on this switch is corresponding to the power rail. So whenever I'm pressing it, you can see that the C1, which is nothing but so for you to visualize, I have logically connected these two by naming them with same net names. here you have C1, and here you have C1. So whenever I am pressing this, what is happening is this row is shorting this column. So whatever the power that is getting transmitted to this LED and through to the ground. So if I am pressing C2, I am getting the D2. If I am pressing C3, I am getting the D3. So this happens with any row and any column. So for example, if I want to enable row 3, I have enabled it, and now if you check, we have the same thing. So the problem with this is, let us say I have enabled all the rows, and now if you press the key, any key in the column, irrespective of the row number, only one LED is glowing. In this scenario, how to differentiate which LED is glowing? So for that, what we will do is focus properly. This is the key part which we will be using for developing Keyscan algorithm also. First, we will be setting all the rows, either to we will be setting them to 0 or 1 based on the configuration of C1. If you are configuring C1 as a pull up pin, pulled up input pin, we have to set the rows to 0, because when the pin is by default pulled up, that is when the pin is by default reading logic 1, in order to observe a change in the pin status, we have to always pull the pin to logic 0. So if you are pulling up the column 1 pin internally, then you have to ground this. If you are pulling down the column 1 pin internally, you have to pull up this. I am assuming that I am pulling down the column pin internally, so I'm enabling all the rows. Now whenever I read something on a column, for example, I read C1 because D1 is glowing. Now what I will do is, I'll disable all the rows, I'll enable row by row. Let us say I'm starting with R4, I'm enabling row 4, and the button is still pressed. So for example, I'm pressing R1 still, so I don't read anything on the C1 pin. For example, now I'm disabling this and enabling this R3 and checking if something is there. So still I'm not getting. Now I'll disable R3 and enable R2 and check if I'm getting. So nothing I'm getting. Now I'll enable R1 and check if something I'm getting. So I'm getting C1. So now what I have to conclude is R1 C1. This is the corresponding position of the button that the user is pressing. In this way, we will be writing an algorithm which will enable row by row and check the column for the input. Whichever the column which is giving the input for a particular row, that column and that row combined will give the position of the key that the user is pressing. So now let's move back to the Keyscan algorithm. So in the previous session, when I was explaining, I told you that if the column pins are pulled up internally, we'll be using logic 0. If they are pulled down internally, we'll be using logic 1. So in our case, we have pulled up all the column pins. So we'll be using logic 0 for the rows. So configure rows as outputs and columns as input, and then make all the rows as 0. Why we are doing this is, for example, let us say if user is not pressing any key, it is a waste of time enabling and disabling the rows and checking for columns. So what we'll do is we'll enable all the rows and check if at least one column is giving an input. If at least one column is responding, then we will disable all the rows and enable the rows one by one to know which column is being which row is being corresponding to the column. So wait until any one of the column pins becomes 0. So once you have enabled all the zeros to disable all the zeros to 0, all the rows to 0, if any one column pin is becoming 0, that means the user is pressing a key on the keypad matrix. Once any column pin becomes 0, what you will do is you will disable all the rows at once. That is, you will make all the rows to once, and then what you will do is you will make each row by row 0 to know which column is being pressed. Let us make R1 as 0, check C1, R2 as 0, check C1, R3 as 0, check C1. In this way, we will be repeating for all the rows. Once you find the exact position of the button that the user is pressing, now what you will do is you will return the corresponding uh, letter. That is, for example, if you see in the first slide, so here we have the positions. Let us say R1 C1 corresponding to 1, R1 C2 corresponds to 2, R1 C3 corresponds to 3. In this way, we can maintain an array, or we can just simply return a number whenever R1 C1 is pressed. You return 1. R1 C2 is pressed. You return 2. In this way, you can devise a function and name it as Keyscan. So once you are done with finding the position, just return the number, and this is what the Keyscan algorithm is. So next, coming to the Keyscan logic. So if you observe here, what we are doing is we are like we are enabling all the rows, and we are waiting until at least one column is delivering. That is what we are doing is, so if you observe here, what does 0x70 mean is, so we have connected all the rows to first four bits of the uh, here we have connected column pins, that is C0 to C3, to PB4 to PB6 pins of our STM32. So now what is so this is the idea. So we have connected the pins in this fashion. So from here to here, from 4 to 6 we have connected. So if nothing is being read, all the three pins will be 1 because we have pulled up them. So if you write the hexadecimal equivalent, it will be 0x70, because these 4 bits will we are not caring. So 0x70. Now what we are doing is, until any key is pressed, that is if the IDR value is still 0x70, we will be waiting here. It is a simple bodiless while loop, so we'll be hanging up here until someone presses a key. What does this AND do is, simply it will copy the values of the register at the corresponding positions that we are needing. So we need the at the position 0x70. So whatever the value it is there it will be copying. So coming to the next part will be, if anyone presses a key, this while loop will be exited because the value will no longer be equivalent to 0x70. Now what we'll do is, we'll clear the last two bits, that is we'll clear the last four bits, which are our row bits of the ODR, and load it with E. Why E? So as I mentioned earlier, we will be moving row by row. So if you observe the binary equivalent, this is the first value uh, that we will keep, that is 0x00. So sorry, 0x000, and the next value will be enabling row 1. So if you keep this 1 and keep the remaining as 0, this will give you a hexadecimal equivalent of, this will be E. Sorry, just a minute. So this will be E, and if you shift a row little further, so this will be nothing but, if you see, this will be B, sorry, D, and then 1011, which is B, and finally it will be 0 double triple one, this which will be 7. So EDB7, these are the values that we will be loading into our rows in order to disable row by row and check the columns and know which key is being pressed. So let me explain you for one cycle. So what we are doing is, we are enabling only one row, that is we are placing 0 at only one row, which is our R1, and what we are doing is, we are reading the value present in the IDR register. So we are performing a AND operation with 0x70, that is whatever the values present in the particular positions, that will be exactly copied into the temporary register. So what happens is, based on the value of temp, if it is 0x60, that is 110 101 011, these are the only three possible values that can be. If this is the case, column 1 is pressed. If this is the case, column 2 is pressed. If this is the case, column 3 is pressed. So based on our first diagram, row 1 column 1 corresponds to 1, row 1 column 2 corresponds to 2, row 1 column 3 corresponds to 3. In this manner, we'll be repeating with all the 4 rows to know which key is pressed. At the end, what we'll do is, we'll just simply close the loop, because we are already returning the values here. So if you see here, we are returning every value that we are being if it is matching. And coming to the next part, the next part is scanning the key and putting into the ODR. So this is a like normal while one loop that we'll be using in every embedded program. So key scan. Once you get the key into the key variable, what we'll do is, we'll perform a, first we'll clear the bits of the ODR, first 4 bits, for that and equal to negation of operation as discussed earlier, and then we'll shift the bits by 12 times, because we are expecting the number to be of 4 bits, but the port is of 16 bits, and we have connected the LEDs to the first 4 bits. So for that we need to shift this to by 12 times, so that all the 4 bits will be in the first starting from the 16th bit. and then we'll introduce a delay. This delay is, as mentioned earlier, software delay to avoid key debouncing. So this is the final code. So this is the ms delay function, and then you have your key scan logic. And once your key scan logic is done, we have something known as keypad init. In keypad init function, what I have kept is whatever the motor register configuration, those all I pushed it in the keypad init. You can keep them in main also. And once you're done with it, we have our while one logic wherein we'll read the key and push it onto the ODR. So let us see the final code and simulation. So this will be our final code. So we have our ms delay function, key scan logic, and then we have keypad init and our main function. Once you are done with writing the code, you have to click on compile, translate, and then build. Go to flash, configure flash tools, and then in the output you have to ask your compiler to create the hex file. You have to tick this and name your hex file with a proper name. And once you are done with it, you can move to your Proteus file where in which your schematic is ready. You can double click on it and add your hex file here, and it is already loaded in my case. So you can start simulation. And once the simulation is started, so when I'm pressing 1, you can see 0001, which is equivalent to 1, and then 8. So you can see 10008 9 1001, and then you can check for any key. So this means our keypad driver is working well. So yeah, this is for this video. If you like the video and find this video useful, please do share it with your friends, and like and share my video with your friends. Please subscribe to my channel Tech Talks for more interesting videos like this. Thank you.